Alright, the purpose of this video is just to get you a lot of repetition with the chain rule. We're not going to get into the super hard examples where you have multiple rules inside rules. That'll be in the next video. In this one, it's just getting comfortable with the basic chain rule because the basic chain rule is hard enough that it's going to take some getting used to. In this first example, we're trying to find the derivative of e raised up to the 5x power. The way you want to view the outer function here is e raised up to the stuff is the outer layer. And the inner layer is that stuff, the 5 to the x power. I know that's really hard to see, but think about it like this. If f of x were equal to e to the x, and g of x were equal to 5x, think about what you would get if you were trying to figure out f of g of x. Take these two functions and compose them in this order, and I think what you'll find is this right here. So the outer function, the f, corresponds with this e to the x, and the inner function, the g of x, corresponds with this 5x that you see up here. Anyways, when you're taking the derivative, the way to think about it is if it were the derivative of just e to the x power, the derivative would just be e to the x power. But it's not, it's e to the 5x. So the derivative is e raised up to that stuff, 5x in this case, but then I'm not done. I have to multiply that by the derivative of that stuff, the 5x. Here is f prime of g of x times g prime of x. And when you get the hang of this, you'll be able to do all that in one step and recognize that our answer is just e to the 5x times 5. In other words, 5e to the 5x. This is a weird thing to write in a math class, but maybe it's helpful for students if you're taking the derivative of e raised up to stuff, where stuff represents some function. The answer is going to be e raised up to that stuff times the derivative of that stuff. This isn't some new rule. This is just the chain rule. It's just how the chain rule ends up working with e to the x as the outer function. Let's try another problem. What if we're figuring out the derivative of 5 divided by natural log of x? First comment, you could absolutely use the quotient rule if you wanted. In fact, I'd kind of argue that this problem is maybe more naturally suited for a quotient rule. And using the quotient rule on this one will work out all right. It won't be that bad. But you don't need to use the quotient rule. And I think once you get the hang of the chain rule, you're going to prefer that whenever possible to rules like the quotient rule. Chain rule is much neater, much cleaner than the quotient rule is. How would you use the chain rule here? Well, you'd have to rewrite this problem so that it's a function inside of a function. How would you do that? Well, we could think about this as the derivative of 5 times, instead of divided by, the natural log of x raised up to the negative 1 power. Because when you raise something to the negative 1 power, it's the reciprocal of that thing, and that produces this 1 over natural log of x, which ends up down here. When it's written down here, maybe it's a little bit easier to see the chain rule. We have this constant, this 5, that we can just pull right out in front, but then we'll need to take the derivative of what's left behind. And what's left behind is something, natural log of x in this case, raised up to the negative 1 power. That natural log of x is going to work as the inside layer, and that raised up to the negative 1 power is going to serve as our outer function. How do we take this derivative? We'll leave the 5 completely alone. Then we'll take the derivative of the red layer, so bring the negative 1 down in front, and then subtract 1 from that exponent. That's the end of the red layer, but the red layer has to be evaluated at the blue layer. In other words, you leave the natural log of x stuff completely alone, and then you multiply by the derivative of that blue stuff. The derivative of natural log of x is 1 over x. You could use the quotient rule to get this derivative, or you could use the chain rule, and it would end up looking something like this. You could leave this just as it's written, or you could rewrite it by taking the negative 5 and throwing it on top of the fraction. The x is down on the bottom of the fraction, and natural log of x raised up to the negative 2 power is the same as the natural log of x squared down on the bottom of the fraction. Calculus is done in this step, but if you want to flex some algebraic muscle, you can simplify and get a slightly prettier answer like you see here. And if you really want to show off, use the quotient rule, get that answer, and convince yourself that that's equivalent to what you see here. You have to do a little bit of algebra to manipulate stuff to make it the exact same. But it's not a bad exercise to do if you have the time and desire. Let's move on to another example. This looks really hard. Turns out it's not. The derivative of e raised up to the 5x squared minus 7x plus 1. Really, that's just this case, the derivative of e to the stuff. And the answer for that derivative is e to the stuff times the derivative of the stuff. Why? Because all we're doing is we're taking f of x equals e to the x, and g of x is 5x squared minus 7x plus 1, and we're composing those two in this order. You will get to the point in this class where you see a problem like this, and it's a one-step immediate answer. You just like this, e to the 5x squared minus 7x plus 1. times the derivative of 5x squared minus 7x plus 1, which is 10x minus 7. You'll get to the point where you can see this. And when you get to that point, or if you're already at that point right now, you should pause and marvel, because that's pretty damn impressive. The level of calculus required to figure out this derivative is kind of mind-blowing. But sometimes that can get lost because we build up things in so many steps in this class. There's a lot that goes into getting this answer. There's a lot that goes into just getting this part of this answer. And if you're keeping up in this class, you should be really proud of yourself. This is something that a lot of people can't do. Anyways, that's enough of a pep talk. Let's do a couple more examples, then we'll call this video good. Here's another example where you could do this problem multiple ways. One way, which may be the most obvious to some students, is to use the quotient rule. Got a function on the top that's just a constant and a function that's down on the bottom here. You could do that, but when you're using the quotient rule, you'd have to take the derivative of the bottom here. And when you're taking the derivative of the bottom, you're going to end up having to use the chain rule anyways. So one option would be the chain rule inside of the quotient rule. That's going to be nasty. But a better way to do this is to recognize that we can rewrite this expression as 8 plus 8 times the log base 8 of x, sorry about that, raised up to the negative 1/2 power. Why negative 1/2 power? The 1/2 for the square root, the negative for the fact that it's down on the bottom of the fraction. Can you get this without me color coordinating things? Can you see how these parentheses and this exponent would kind of be in red with our color coordination? So if we were using the chain rule, we take that exponent down in front, and then we'd subtract 1 from the exponent, and then we'd leave the inner layer, which would be in a lighter blue, completely alone. 8 plus 8 times the log base 8 of x. But then we wouldn't be done. We'd have to multiply that answer by the derivative of this stuff. What's the derivative of this stuff? Well, I have two different terms, so I'm going to take the derivative of each term individually. The derivative of this term is just 0. For this term, I have an 8 that's a constant that I can pull out in front, and then I'm going to multiply that by the derivative of the log base 8 of x. What's the derivative of the log base 8 of x? It's 1 over x times the natural log of 8. So the derivative of 8 plus 8 log base 8 of x is 8 times 1 over x times the natural log of 8. You could clean this up a little bit if you wanted to. I mean, maybe throw this 8 up on the top here. Get rid of this negative exponent. Sure, I'll do it. I got a negative times a positive, so the whole thing's going to be negative. I'm going to have a big old fraction because there's some stuff on the top and some stuff that's on the bottom. I think the only thing that's on the top is this 8 that you see over here. Down on the bottom, I got 8 plus 8 log base 8 of x, all this stuff, raised up to the negative 3/2 power. The negative is already taken care of by the fact that I put it down on the bottom here. Raising it up to the 3/2 power means cubing it for the 3 and taking the square root for the 1/2. That square root ends right here, and then I have to multiply that by x times the natural log of 8, all the stuff that's down in the denominator over here. Maybe this is a little bit prettier than what you see here. Again, if you go from here to here, that's great. But for our class, you can call this good and just move on to the next problem. And hey, I got some good news. The next one, the last one that I have here, we already did that up here, right? So I guess I meant to change that or something and I didn't. So what that means is this video is completely done. And in the next video, we'll move on to more difficult chain rule examples. And I know that sounds kind of scary, but if you can do this level of chain rule, you'll be totally fine in the next step. This is the foundation that it'll be based upon. And if you've gotten this far, you'll be able to finish it. Trust me.